Alright, so welcome everyone to Trunova-AI. In this channel, we try to break down into the actual AI system and see how it actually works, and we try to burst some myths which is all around the world today regarding AI. So, in the first episode, we'll be mostly talking about why LLMs are just probabilistic systems and why that matters. So, basically, what happens is people say large language models can reason, and some people say that they are just autocomplete models on steroids. Well, both are partially correct and both are partially wrong, but they both sound very confident. In reality, both these explanations are incomplete. In this video, I want to show you something simpler and more useful. Modern LLMs behave like probabilistic models, probabilistic systems, and we know that we have been building these probabilistic models and probabilistic systems for like decades. And if you misunderstand that, you'll design bad prompts, you'll design broken products, and unrealistic expectations will be set for the AI. And yeah, so we need to understand how this LLMs actually work and what it is. So by the end of this video, you'll have a mental model about the LLMs and you'll know what actually happens. So let's try to see what happens in when we use an AI. So basically, we are just so what happens when we are using any LLM, that there is some sort of AI model black box. Let's say this is a some AI black box. We provide an input like how we talk to ChatGPT. Then something happens here in this AI black box and we receive output, right? Most people think that this AI black box is actually thinking, it is actually reasoning, but this is not the case. It's not thinking. There is no reason, there is no thinking involved. It is just a probabilistic model. And whatever we see, whatever output we are receiving here, this is just a sample of tokens based on some probability distribution. Like, and this is not a new idea. So long before ChatGPT, we already had systems that predicted what comes next. So basically, imagine if you have word one, then you have word two. So based on this word one and word two, what will be the suppose you have five words, and I ask what is the probability of all the five words to coming in this third position, given that we have word one and word two. For example, if I say I am, and if I ask what will be the third word, and I give you some options like happy and play, like these are verbs. I let's say another verb, and let's say verb in a different form. So if I ask what should be coming here of these four words, which word should be coming here after I am? So as human, we because we understand the nature of English grammar, we will say that okay, I think happy should be coming here, and running is another candidate. So these two make sense to appear here. But I am play, I am it doesn't make any sense. Now let's say if I put here happy, right? And I give you another option here. Now I ask, okay, based on these three words, I am happy, what should be the fourth word? So we see I'm happy, happy. No, I'm happy, play. No, I'm happy, eat. No, I'm happy running. Maybe, but I'm happy today. Yeah, that looks the best candidate for this position. So this is how the early language models used to work, and they were like mostly probabilistic models, and like not mostly, they were all statistical probabilistic model. And we used to find out the probability of each word in a vocabulary, to check which one has the highest probability, and then we say, okay, that word deserves to be here. And there were like different algorithms, different concepts in statistics to find the probability of the next word given the previous words. So this was the core concept, and this is the core concept in probabilistic distribution. So basically, LLMs didn't invent prediction. LLMs are simply scaling this based on different new experiments, different new findings. So the core concept remains the same. Now let's try to zoom out a bit and understand the developments using a timeline. So imagine we have a timeline here, and let's say these are the milestones of development, right? Now, in the very early stages, what used to happen was there were if and else conditions, right? And these if and else conditions were like very brittle and hard rules. We as programmers, we write if and else conditions in our coding scripts, and we know that how brittle these systems are. Then came decision trees, and these are still rules, but with a lot more branches than if and else condition. Then came the first model where we started assigning probabilities, so statistical models. The next development was the game changer, neural networks. Everything changed from here. And whatever we are doing today is based on neural networks. So let's say LLMs stand here, right? So this was the first time when we started assigning probabilities, and this was the first time when game changed after the development of neural network. Okay, but the key concept here to understand and to look for is at every step we are replacing certainty with probability. At every step, what do? We are replacing certainty with probabilities, and these are like this is the most important concept to grab from here, right? Okay, so now let me try to explain how did we jump from statistical models to LLM, like what happened during this phase. Okay, three important concepts here, and with these three concepts we can understand how we developed from probabilistic statistical models to current generation LLM. So the first is Markov chain, then the second is engrams, okay, and finally LLMs. Okay, the arrow is for developments which happen from Markov chain to engrams, and from engrams to LLMs. Okay, to understand about Markov chain rule, let me take an example of weather. Let's say today's weather is sunny. What will be the weather tomorrow? So we have, say, three possibilities, right? One could be rainy, the other could be cloudy, and the third possibility could be sun itself. So what Markov chain does is basically it doesn't know for sure what would be the chances, right? So what Markov chain does is like it only cares about what is happening right now, like what is happening today. Today is sunny, right? So Markov chain will guess the next prediction based on today's weather. So it would say, okay, I think sunny has the maximum probability. Sunny would be, let's say, according to Markov chains, there are 70% chances that tomorrow's weather would be sunny, and it would assign lesser probabilities for cloudy and rainy. So basically, what it did Markov chain simply looked at the current state to guess the next state. That's the core idea of Markov chain. It doesn't care about what happened yesterday, what happened in the last week. No, it doesn't care. It just looks at the current state, today's weather, and it will predict tomorrow's weather, right? Now let's see that example of an English sentence. I am happy. So Markov chain will look at I and it will predict, okay, so maybe the probability of M would be the highest. Then it would look at M and then it will decide the probability of happy. So it goes something like this, right? Uh, but Markov chain guess the next thing only using one current element, one current thing. It doesn't take into account like more than one thing or more than one state. So that is the point when we jump to n-grams. So let's take the same example. In n-grams, what happens is I will just paste this here and here and here. So given I, n-gram predicts, okay, the next word should be M. But what if we have two words, I and M? Then it will predict, okay, happy. It will give probability, highest probability for happy. Now, it took two words into account. That's the key idea. It took two words into memory, not just one word. Now, if we have I am happy, three words, and we want to predict what would be the fourth word, right? Then it will take all these three words into account and it would say, okay, the next word should be, let's say, today. So here, it had like one word. Here it had two word, and finally it had three words. So you see, in n-grams, we are not looking at just the previous or current state. I mean, not just on the current state, but we try to keep into memory like all the previous states, whatever has occurred. We can define the window of the n-gram. It can be, let's say, two words, three words, and we can increase that as many times as we want. So basically, the main difference is Markov chains remember one thing and n-grams remember more than one thing, right? So the key idea here is, what is the key idea? What pattern we can see from here? So the most important key idea here is more words give better guesses, and we should all agree on this. We should all agree on this. This is the most important idea we can infer, because Ingram started performing better than Markov chain. That's why we can infer this. But there is one very big problem here, and the problem is this thing: more words. So more words means too many combinations. More words mean Too many combinations. Now, there's too many combinations of because language has too many possible sentences, and when we try to remember many words, the number of combinations becomes too big. And if there are too many combinations, then what will happen? Then our computer gets overwhelmed. So we don't want that. So Ngram basically works, but for small problems. But we started solving very big problems as time progressed. So that's when this LLM starts showing magic. So till here in till ngrams, what we used to do, we used to store the probabilities of a table of probabilities for different word combinations. But in LLMs, we do not store anything. But instead of storing the tables of probabilities for different combinations, what we do, we try to learn patterns using neural networks. So neural networks, that's the key concept here. So the idea is same, but the brain has become bigger here. So till here we were not using neural networks, we were using statistical models. We were storing probabilities of different combinations of words, and but here in LLMs we have neural networks, we have weights, and we try to learn weights, and these weights predict the next best token. And so what we from Markov chain to ngrams to large language models, we see what we let me explain what we did here. We guess the next thing here, next thing in Markov chain. What did we do here in ngrams? In ngrams also we guess the next thing. Then what we did do in LLMs? In LLMs as well, we guess the next thing. So that is the key thing. That's what I was trying to explain. The goal never changed, only the method improved. Earlier also we were trying to guess the next thing, here also, and in LLMs as well. But in earlier technology, earlier tools, we were just looking at the current state, but in ngrams we started looking on more states. In LLMs, instead of storing probabilities, we started learning patterns using neural network. And to learn these patterns, we use a very huge training data set, like training corpus. So basically, LLMs are not magic. They are very good at guessing what comes next.